Hello and welcome. My name's Andrew, and the following video has two purposes. Firstly, I'm submitting it as a computer graphics research assignment or project, and secondly, I'm also putting it on my channel because I think it's kind of cool. So recently I've been working on a video game project, and the purpose of this project is to add to that project basically some more advanced texture techniques. So here's an overview. I've developed a basic game system which works, and I've got that up and running. Okay, hi, so this is just a quick demo of the basic underlying game system that I created for this project. It's nothing too fancy, so this was done in Python. We can fire it up, and we have a bunch of different coordinate systems, view coordinates, projection coordinates, as well as down below we have some status about the game. So at the moment, if I walk here, we have rooms which are visible regions, and then visible regions are split into sectors. So the little rectangle that we're in at the moment is red. That's the sector we're in. That's for collision checking. So we do not have to do collision checks with every single object in our game. That would be too much. We can also keep track of which sector we're in. Over here in yellow we have a door. As we walk up to it, it opens up and we see the rest of our room. So we are trying to reduce the overdraw. Also kind of looks pretty cool. Okay, so yeah, we can see with a larger level, we are within reason reducing the overdraw. Just doing basic backface culling. This is all done by hand without OpenGL or anything. And that's it. So that's the game system. So in addition to that, I wanted to create a level editor which would be useful even moving beyond the basic prototype. So I made this in tkinter. It's reasonably large at the moment, 1300 lines of code. That was fun. So if we run this, at the moment we haven't got anything, but we can go ahead and make something. So we can say, okay, let's make a sector. And we see it down here, and let's just update some of the positions. So I'm going to set the X to position 6, the Y to position 12, and I'll give it a width of 5, a height of 2. Hit update sector and it snaps in there. I can give it some walls, and we see the walls are indicated in red. I can create another sector. Now I'll put this sector just next to it, so I'll set its X to 6, its Y to 9, because we want to give it a little bit of separation. It doesn't matter, let's set it to 5 and height to 3. Okay, so we see we have these two sectors next to each other, but they are separate. So here's the cool thing. This automatically detects when things are in separate rooms. So at the moment we see here we are in sector 1, and that is in room 1. But if we flip back over, sector 0 is in room 0. So there's a little algorithm that's detecting that those rectangles are partitioned from are separate, disjoint from each other, and it sets them to different rooms. We can play around with that. We can take sector 1 and we can shift it upwards by 1 unit. And now when I click through them, they are both set to room 0, as they should be. They should be in the same room. But we can go to sector, well, it doesn't matter, we're in sector 0 at the moment, put a wall between those, and now sector 0 is in room 1. Oh, that's strange, they've both been set to the same room. So let me just try that again. There we go, hit update sector again. Sector 0 is in room 0, sector 1 is in room 1, so they're disjoint from each other. Okay, I just realized the reason that it set them both to the same room was because I only defined a wall on one of the sectors, and it just takes a double click. When I was making these, so I'll try this again. We put a door between them, so sector 0 is in room 0, sector 1 is in room 1, and it has detected that sector 1 has a door on the north boundary. So again, it also sets things up so, you know, sector 0 had a door, I put that on the south boundary, and it automatically added a door to sector 1's north boundary because those sectors were joined together. So this is a cool little system, and it's really cool because it's better than doing it by hand. It's a lot of work. Drawing things out on paper is fun, but not when you have to make 20 levels. Cool. Yeah, so that's just a basic overview of the existing system, and then the rest of this video will be talking about the graphic stuff. And then I sent it over to C++ and OpenGL and started playing around with that. Well, I created just a white box system to check that everything was stable and good, and then I added some textures, and then well, I don't really have models yet. I haven't designed those, so I just worked with rectangles, but I got some basic logic going for guns and enemies and shooting enemies and all that sort of fun stuff. Okay, so with that out of the way, we'll get to the meat and potatoes of this project, which is the textures. Okay, take 3. So here is the program as it stands at this point. It's getting quite large, so this isn't really graphic stuff yet, but I'll just note that I applied the model view control design structure, a design pattern, to my work. I decomposed everything out into classes and then separated them. So the model classes are basically all of the game objects that have individual properties and behavior and everything. The view objects are basically OpenGL sort of stuff, graphic stuff. As much as possible, I passed that off into the view section. So I decoupled an object's behavior from its view. And then control basically has pointers to everything. So that's the main game logic is in the control classes. At the moment, it's mostly just the game app. So let's have a look at the shaders. So I'll just run this. It's a little demo. We load everything up. At the moment, we're using about 1 GB of RAM. We can walk around and we see lights. It's cool. It's very spooky. These gray colors are doors. I haven't implemented anything yet, but at the moment they're just, you know, it's screen's not being drawn to, or screen is being drawn to. I'll fill that in later. So we jump in here, and it's very cool. It's kind of Egyptian, and yeah, it's fun. It's nice. I really like that shot. But anyway, so shaders. There's a few of them. Note that the gun was just a box, a rectangle with nothing else applied, just a matte kind of color. So that's where this colored 3D shader comes in. It just applies a basic model view projection transformation stack and passes the position through. And it takes the color and just passes it through with no transformations. Then in the fragment shader section, there is a bit more code here, and the reason for that is I tried to implement Bloom. I wasn't really happy with it. I will give it another shot. At this point, it's not there, but So what I was trying to do was separate, so basically pass through the color, make no change to it, but then separate out, you know, the bright colors from the dull colors, and then the bright colors have bloom applied. It didn't work out. But moving on. So then I have a 2D shader. Now the reason for that, in one of the videos that I popped up before, we had an enemy that was throwing fireballs at the player. And when the fireballs hit the player, a bunch of effects were applied. First of all, we had a monochrome effect, which was tinted with kind of a purple. And then we had an edge filter, which was tinted with a green, because, you know, purple and green are complementary colors. So I thought that was cool. But in order to do that, we need to apply post-processing effects. We render the whole screen every frame, but we render that off screen as a texture, like a virtual texture. And then we draw a textured rectangle which fits over the whole size of the screen, and the texture that we splat on there is the pre-rendered texture from the first pass of the render. This means that we can apply post-processing effects to the whole image as if it were just a two-dimensional image. Cool. So I achieved that with kernel effects, which basically take a weighted average, kind of an average, of the, or a linear combination, I'll say that, where each entry in this matrix here is the weight which is applied, or the coefficient which is applied in the linear combination to neighboring pixels. So for instance, if we want to do an edge filter, well, we take the center and then we subtract each of the neighboring pixels. If we want to do a blur, well, we just kind of take an average of all of the pixels and we change the weighting so that the center pixel is weighted a little more. But it's just a stylistic sort of thing. Then I did apply some gamma correction here, but it's basically color correction, so nothing too crazy there. But anyway, so there we have that bit. Now for the main, bring this up. For the main shader, really this is where most of it happens. So we take in a bunch of bits of information. Now this normal, tangent, and bitangent are used to transform coordinates into tangent space. And what that means, really, my report goes more in depth in it, and I will be going more in depth in it in future videos. But basically, we want to track, so say we have a light and we know the position of the light. Well, we don't, it's all well and good to do it in world coordinates, but if we do it in world coordinates, then that could involve passing in the position of the light to the fragment shader, which does transformations many times, you know, for every single pixel. It's too much. If we can do it in tangent coordinates and then pass that in, well, it minimizes the amount of calculation, because that calculation is just done once per vertex, which is much more efficient. So long story short, we have this tangent, bitangent, and normal, which we can use to set up a transformation system to see how a position is tracked relative to the orientation of a surface. I know it's not very in-depth, but my report covers this more clearly. Anyway, okay, so we do some transformations to the texture coordinate. Well, the texture coordinate, I think, just gets passed in with nothing done to it. Yeah, okay. But we transform the position of the fragment, as well as the light position as well. Anyway, so that gets passed through. I realize I'm starting to ramble a little bit. I'll reel it in. I'll focus on the important stuff. So I'll just bring this up because it's useful to refer to it. Okay, so We have this material structure, and that basically holds a bunch of textures. So I'll open this one as an example. Normally when we draw a texture, it's just this. It's just an image. And that's well and good, but we can improve the quality a little bit. So this thing is called an albedo texture, sometimes called a diffuse texture, and that is the surface, the way it appears under normal lighting. So when we apply diffuse and ambient lighting, we are just sampling fragments from that texture. So if we jump in down here and we look at the calculate point light function, we have a diffuse section and a specular section. Also, earlier in the main function, we have an ambient lighting, but that is applied just once. We don't need to do that on a point light basis. Okay, so the ambient lighting takes an ambient level and multiplies it in with the sampled albedo texture. Same sort of thing for the diffuse lighting that is based on the albedo texture. The next map is something called a specular texture. So if I open this up, very interesting. So there are two types of lighting. Diffuse lighting is more or less applied to the whole surface, and specular lighting is a kind of more intense, kind of reflective lighting. And we need to define how light interacts with a surface. So in the case of a specular light just being like a black and white image, the light which is reflected is the same color as the light which is coming in. However, metal surfaces have a tendency to tint the light which is reflected off them. So if I look at this clean copper and I look at its specular map, it has kind of a coppery kind of tint. So if I shine I don't know, like a green light, I shine a green light on the copper, it will come in and the green will multiply with this bluey color, and that will be the output. So metal textures tint the color of the light which comes into them. Okay. What else do we have? We have a normal texture. So by default, and by the way, this is what a surface looks like when it's mapped in tangent space. It's always facing directly back at the viewer, more or less. Okay, so by default, surfaces are set up with the positive z coordinate pointing towards the viewer. Now we could define a single normal, or we could define a normal on a per pixel basis. So looking here, we have red, green, blue, x, y, z. So z is the blue component, which is the reason that most of this is blue, because most of it should be pointing, normals should be pointing directly back at us. X is red, so on the kind of horizontal boundaries we have a variation in the red component, left or right. So pointing to the right, that's a positive X, we have a bit more red. Pointing to the left is a negative X, so a bit less red. And then green as the second component is Y. So, if we're pointing upwards, we'll have a positive Y, so a bit more green there. And downwards we have negative Y, so a bit less green. Long story short, this defines the normal vector of a surface on a per pixel level. So if we look back at our shader, it will need a normal vector, and we get that normal vector by sampling the fragment from a material's normal texture. Okay, that is used in both the specular and diffuse lighting. Cool. Okay, so what do we have next? We have ambient occlusion. So it turns out when we have a surface which has a bit of what we would call internal geometry, so some creases, some bends and things, there's a tendency for the surface to cast shadows on itself, even when it's under full lighting conditions. So if we open up this ambient occlusion map. It's mostly bright, which is no variation whatsoever. However, around these creasy kind of areas, there's some natural shadows which are defined. So the way we apply this is we multiply it on a per pixel level with the output of the shader. So let's say, for instance, I've commented this out. So this should be running without any ambient occlusion. And we can kind of walk here, and here's a texture. It's you know, there it is with no ambient occlusion. Okay, now we sample that ambient occlusion texture. It's just a single channel texture, so we just take the first channel, the red, and multiply that in. And this is such a subtle effect that the texture I picked, it seems to make no difference. However, on on the whole, this does improve the quality of textures. It works, trust me. Okay, so what else do we have? Well, we've got glossiness and height. So glossiness defines, well, in this case, I took glossiness to define the shininess of a pixel. So in the specular lighting calculation, there is what's called a shininess exponent, which raises the power of a calculation. And it has the effect that when you dial up the shininess, a surface, the reflected light will tend more towards a point, like a single point. And when you decrease the shininess, the surface overall looks a bit rougher. Like the lighting which is reflected spreads out, kind of like if you shone a light on a really rough surface, you wouldn't get an exact reflection, you get like a spread out reflection. So what I did is I sampled from each of these points, which gave me a number between 0 and 1, and I multiplied that up by, well, in this case I think I multiplied it up by 32, because I was finding that if I went any larger I would get weird effects. But just for fun, let's make this larger. So we're increasing the shininess of all of our surfaces, and hopefully this works. Hopefully. So this is a little hard to see, but if I look at this wood, the wooden parts seem to I don't know. It's very subtle. Wooden parts seem to respond a little more. I don't know. It's not really working so well. This is not a good demonstration. Let's dial that back to 32 and just say that it works. Okay. Right. Last of all, we have height map. So height map approximates an uneven surface by defining like little height deflections, and then there's a number of calculations we can do to again approximate a three-dimensional surface. So there's something called parallax mapping, which I go into more in depth in my report, but what parallax mapping does is it adaptively selects different texture coordinates. It transforms the texture coordinates to mimic a three-dimensional surface. So let's apply that. So now instead of just taking the regular texture coordinates, we run this parallax mapping function, and that gives us a new set of texture coordinates. And sometimes this works, and sometimes it doesn't. So if I go over here, we can see that now it's mimicking a three-dimensional surface. So it's pointing out at us a little bit. However, this might need a little tweaking. I've looked it up online, and this algorithm is very subjective. And as we can see here, there's a disconnect, and this is not working. This is not working very well. Furthermore, if I look over here, this is kind of coming out towards me, which is what it should be doing. But if I look in the other direction, it is kind of mapping that away from me, inwards. I'm not really sure why that's happening. And at this point, it's not really worth my time to look into that. So there are other things that I want to work on before I worry about that. Specifically Bloom. I want to get Bloom working, and I also want to be loading in models from object files, which, yeah, I know how to do that. I mean, it's not too hard to code that up. It's just simply the next stage of the project. Okay, so that was just a really quick overview of how we can use a variety of texture maps to get some things popping, get some things happening, and improve the quality of our graphics. So hopefully this was useful. Hope you had fun, and yeah, all the best. Thanks for listening. All right, bye. Oh, and side note, for my regular videos, I will be getting back to that very soon. I've just been crazy busy with assignments and exams. Doing pure math with an overloaded schedule means that when final exams come, it's all you can think of. But yes, I will be getting back to regular, Vulkan and OpenGL tutorials really soon. All right, thanks a lot. Bye.